Welcome back to JVM Internals Crashcasts. I'm Sheila, and with me as always is our JVM expert, Victor. Today we're diving deeper into our garbage collection deep dive chapter, focusing on GC tuning and monitoring. Victor, are you ready to help our listeners optimize their JVM's garbage collection?
Absolutely, Sheila. I'm excited to share some insights on this crucial aspect of JVM performance. It's a topic that can make a significant difference in application efficiency.
Great. Before we jump in, let's start with a quiz question for our listeners. Here it is. What percentage of your application's total execution time should ideally be spent on garbage collection?
Ooh, that's an intriguing question, Sheila. It really makes you think about the balance between application work and housekeeping. I'm curious to see what our listeners will guess. Without giving away the answer, I'd say it's a number that might surprise many developers.
Agreed, Victor. Now, let's lay some groundwork. Can you briefly explain what we mean by GC tuning and why it's important?
Certainly. GC tuning refers to the process of adjusting various JVM parameters to optimize garbage collection performance. It's crucial because inefficient garbage collection can lead to application pauses, reduced throughput, and poor user experience. Think of it like tuning a car engine. When done right, you get better performance and efficiency.
That's a great analogy. So, what are some basic parameters we can adjust for GC tuning?
The most fundamental parameter is the heap size. You can set the initial and maximum heap size using XMS and XMX flags respectively. These flags tell the JVM how much memory to use at startup and the maximum it can grow to. For example, XM's 256 mets. XMX1G sets the initial heap size to 256 MB and the maximum to 1 GB. Another important parameter is the choice of GC algorithm, which we covered in our previous episode.
I see. So, if I understand correctly, we're basically telling the JVM how much memory it can use for object allocation. But how do we know what values to set?
That's a great question, Sheila. It often requires experimentation and monitoring. A common starting point is to set the initial and maximum heap sizes to the same value to avoid resizing pauses. As for the actual size, it depends on your application's memory needs and available system resources. This is where monitoring comes into play.
Speaking of monitoring, what tools can developers use to keep an eye on their application's GC behavior?
There are several useful tools. The simplest is to enable GC logging, which records garbage collection events. For real-time monitoring, the JDK includes tools like JStat and JConsole. These let you watch GC activity as it happens. For more in-depth analysis, you might use specialized tools that can visualize and interpret GC logs.
That's quite a toolkit. But once we have all this data, how do we make sense of it?
Great point. Analyzing GC logs is indeed a skill in itself. You're looking for patterns in GC frequency, duration, and the amount of memory reclaimed. High frequency or long pause times are red flags. Also, pay attention to the old generation collection frequency. Ideally, this should be relatively low.
I can see how this could get complex quickly. Are there any common pitfalls or misconceptions about GC tuning that our listeners should be aware of?
Absolutely. One common misconception is that a bigger heap is always better. While it can reduce GC frequency, it can also lead to longer GC pauses. Another pitfall is over-tuning. Sometimes the default settings work well, and excessive tuning can introduce more problems than it solves.
That's really interesting. It sounds like there's a delicate balance to strike. Can you share a real-world scenario where GC tuning made a significant difference?
Sure. I once worked on a high-load e-commerce platform that was experiencing periodic slowdowns during peak hours. By analyzing the GC logs, we found that full GC was occurring too frequently. We adjusted the heap size, tweaked the ratio of young to old generation, and switched from the parallel GC to the G1 GC. These changes reduced our application's GC time from about 10% to less than 2% of total execution time, significantly improving responsiveness.
Wow, that's a dramatic improvement. That really shows the impact of proper tuning. Now, I think it's time to reveal the answer to our quiz question. Victor, would you like to do the honours?
Of course, the ideal percentage of execution time spent on garbage collection is generally considered to be less than 5%. Some experts even suggest aiming for less than 1% in latency-sensitive applications. However, the exact target can vary depending on your specific use case and performance requirements.
Thank you, Victor. To wrap up, what are the key takeaways for our listeners about GC tuning and monitoring?
Great question, Sheila. I'd summarize it in 4 points. 1. Start with monitoring and understanding your application's GC behavior before making changes. 2. Make incremental adjustments and always measure the impact. 3. Remember that GC tuning is about finding the right balance for your specific application. 4. Don't neglect application-level optimizations. Sometimes reducing object allocation is more effective than tuning GC.
Excellent summary, Victor. That concludes our deep dive into GC tuning and monitoring. In our next episode, we'll be exploring the cutting-edge ZGC and Shenandoah collectors. Until then, keep experimenting with your JVM settings, and don't forget to subscribe and rate our podcast if you're finding it helpful. Thanks for listening to JVM Internals Crashcasts.